My name's Matthew Cutler-Welsh. I have the privilege of looking after this place, which basically means that I've waltzed in after lots of other people have done all the hard work to put this together in terms of the building, but also events like this. We do want this to be an interactive session because, like this venue, today is all about moving the industry forward and supporting the industry so that we can all contribute to building better buildings. So we're not going to do that just by listening. So if you do have questions, either shout out or store them up and we'll have a good Q&A session. But we also want to do some practical demonstrations. We've got some sessions we're going to do. We've got a blow door here. So if you've never used one of those, then that'll be a good chance to have a play with that. We've also got our training walls out there so that you can actually have a look at some of the stuff that we're talking about. And for those of you architects who have never actually had a go at installing some of the stuff that you specify, now's a really good chance. So that when a builder says, have you ever done this? You can say, yeah, I have actually. All right, that's enough from me. I'm going to hand straight over to Hartwig. It's a great pleasure to have here all the way from Germany, and he's been on a trip with Jesse and our other colleague, Jesse's at the back there, other colleagues, Sean, who some of you will have met doing a bit of a roadshow around Australia. So they're about halfway through that right now. So it's fantastic that we've been able to convince you to come to New Zealand. So I'll hand over to you. There's your remote.
Yeah.
Thank you.
Thank you, Matthew. Yeah, hello everybody. It's a pleasure for me to talk to you today and talk about what we've done in Germany, not only in Germany, also in collaboration with the United States and others. While Matthew was afraid that you might fall asleep, I'm afraid that I will fall asleep, given the time difference to Germany, 12 hours, quite a lot, but I'll do my best. Some of the slides, or let's say the sequence of the slides might surprise you, also surprises me, just put them together, so we'll see where we get there. Okay, so I take this to advance it. Okay, yeah, that's good. Yeah, I'd like to give you a short overview of our background. I'm working for the Fraunhofer Society. That's the largest research society in Germany for applied research. You might have heard of Max Planck. They're doing more fundamental research. We do applied research. And we are serving industry, also the service sector and public administration. And the Fraunhofer Society has 66 institutes. They are grouped in different groups of what their main research fields are. So there's information and communication technology, life science, microelectronics, light and surfaces. All sounds very interesting, even defense. And we are among the materials and components. So you could say the mixed section dealing with building science or building physics. Our institute was founded long before the Fraunhofer Society existed in 1929 in Stuttgart. There was an institute of the university at that time, and they already worked in the field of building physics that came up during the time. And we have two locations. One is the one in Stuttgart, the original one, and we also built up a field test site in Holzkirchen. We'll talk a little bit more about that afterwards, where we do our in situ field tests. Our R&D budget is about 30 million euros, and approximately 40% of the money comes from the private sector. And we have about 300 people working for us. The main research fields are energy efficiency, that has become very important, I think also very important to you, but also the indoor environment. That's also one field where we do more and more work. Indoor air quality is important, thermal comfort is important there. And lately, we are also doing quite a bit of research in the field of sustainability, because we figured out that our buildings are getting better and better, well insulated, put PV on the roof. So in the end, net zero or even energy producing buildings, so that the energy consumption during the lifetime of the building, the operation time, is not that important, but the embodied energy becomes more and more important. If you think about concrete or steel, you need a lot of CO2, or you get a lot of CO2 emissions while producing that. And if you have renewable materials, it's the other way around. While they grow, they absorb CO2. And when you don't burn them afterwards, when you put them into your building, then that CO2 will be stored over the lifetime of the building. But then, of course, it's quite important that that building is durable enough. You know? And another very important part is when you go to recycling, is that topic here. What do you do at the end of life? You know? There are many building materials that you can not just put on the dump. You can not deposit it easily. You have to do something about it because there are chemicals in it that protected, I would say, the materials against fire and things like that. You probably know that situation. So we have to look forward for more sustainable building materials, for more sustainable construction, in order to have something that also works in the future. These are the core competences of our institute. Just a short overview, 6 different departments dealing with acoustics, energy efficiency, indoor climate, life cycle engineering, hygrothermics, that's my department. Then we have one, they are trying to develop new mineral-based materials, and one that's looking to the indoor air quality and so on. So now to do this, I'd like to go to the introduction of our field test site that was introduced in the 50s. After the World War II, building materials were scarce, so new materials were developed where the thickness of the walls could be reduced. So you needed less material to do the same thing. But there was a problem, because now you had a reduced thickness, you also had a reduced R value, you could say. And we got problems with mold growth and condensation at the interior surfaces of external walls. And the young man you see here who takes surface temperature recordings there is my father. He's now 92 years old. He also worked with this institute, and I learned quite a bit from him. This was a little bit later, 76. You see still all these different test huts. Something new came about. Then we installed our first air-conditioned test hall, because when you just want to test one building material or building structure, and you're more interested in heat and moisture behavior of that, to build up a whole test hut out of that is pretty expensive. So we try to have smaller wall sections that we are, and I hope you can see that here, that you could take out and weigh in order to find out what the moisture content was. And then you put it back in. Something else was, we already got at that time, because windows or glazing surfaces became larger, people wanted to look outside, so we became a summer overheating problem. And in order to test that and find solutions, we developed this revolving test house. So you could put it in different directions. You could turn it south, north, west, east, in order to find out how much solar input you would get. I mean, nowadays all this is calculated, but you need first to do an experiment. And with that experiment, afterwards, you can validate your mathematical tools, your models. This is a more recent picture of our field test site. You see that we have larger installations there, not only these small test huts. We also have here a building where we can do tests of the indoor environment in offices, look at glare and other things. Then when you put the shading systems down, whether you have still enough light. You can also find out whether it's worth it to have artificial light at the same time in order to reduce that solar input and things like that. Then if you have such a field test site and you have these test huts around over long periods of time, then you will discover that you get damage after a while. Sometimes after 1 or 2 years, sometimes after 10 or 12 years. And we found out that we got more problems with damage, moisture damage, when we had insulated assemblies than with the old assemblies that were not insulated. As long as we didn't touch the old walls, they were okay. And when we applied insulation on the outside, inside, or whatever, then sooner or later we got problems, not with all of them, but with some of them. And the question was, why is that? How can you explain it? We wanted to do something good, to have more insulation, also to prevent condensation and mold growth at the interior surfaces. And now our components were not so durable. Short history to the energy efficiency regulations in Germany. You can see here is these were the minimum requirements that were enforced by law. That started in the early 80s. The reason was the oil crisis in the 70s. Before that, nobody thought about energy efficiency. If we have put insulation in our walls and roofs, but that was only for moisture purposes. We wanted to avoid mold growth. That was the reason. Sometimes it was for comfort, but energy efficiency was on nobody's mind at that time. That changed after the oil crisis. So you see some minimum requirements were enforced and they became more and more stringent over time. So this is what the law enforcement was, and this is what we did research. The first idea was, why insulate a lot? Let's just get more sun in. It will heat up everything, and it did in summertime. In wintertime, it was not enough because you realize if you have simple double glazing, we don't have that much single glazing in Germany, but let's say simple double glazing, then you still lose more energy in wintertime through the window that you gain in summertime, even if it's a warm and nice sunny day in wintertime. The reason is night lasts 16 hours, daytime is only 8 hours, so you can imagine that there's a mismatch. So we found out that this was not the best idea, and we found that we have to insulate more, and then once we've insulated, then we can also use some of the solar gains. Now we are here in the region, as I said already, that we have energy producing houses. Already in the 80s, we started to have air tightness regulations because it was pretty evident. If you put insulation on your wall, then your transmission heat losses are reduced, but you still have the same amount of ventilation heat losses, which become now more important than they used to be before. And therefore, air tightness was a good idea. By the way, this arrow here shows you what we actually got. So most people wanted to have something better than the minimum requirements by code. One reason was also that they got incentives. So lower interest rates on their mortgage and things like that. That was paid for by the government. Now, when you insulate, what is happening? Then you will see that the temperature within your wall will drop. If it drops below the dew point of the indoor air, which is pretty easy, So the dew point of the indoor air is around 10, 12 degrees. And in wintertime, even if you have only 5 degrees outside, you will reach that point, then you get condensation. So we actually figured out that what we did with insulation, it just pushes the dew point in the construction. To a certain point, it's good. Didn't want to have any condensation on the interior surface. But now we have to deal with interstitial condensation. So vapor control strategies become more and more important. That's not the only thing. The other thing is that your wall here at the outside also gets colder compared to before. If something is colder, it dries more slowly than something that's warmer. So that's the other problem. And now we had an explanation for the damage cases that we got due to insulation. And this is something of course, it's a sad story. You want to do a good thing, and at the same time, you get moisture problems, but there are solutions to that. And I think this is what I want to show you today. We don't have to put up with that we get now interstitial condensation. No, we can do it differently. We can, if you do a good moisture control design, then things work as well as they did before, even better, I would say. This is an example of green roofs. I will get back to that later on because they have a lot of advantages. Many people, California and maybe also here, talk about cool roofs. So make your roof surface white to reflect the sun back to the sky. The same effect, even better, you get with a green roof, with vegetation on the roof. Because first of all, also there is radiation back to the sky, and secondly, because moisture is absorbed during rainfall and will be evaporated later, so the roof surface temperature might be even lower than that of a cool roof. When you insulate, and I said this before, you get different problems. And one of the problems we got in the 90s was the more we insulated, the more likely the buildings developed growth of algae or fungi on their surface, the facade surface. Why is that? If you insulate, and if you have an insulation layer of 10 centimeters or more, then the exterior surface of your facade is actually decoupled from what's going on inside. There's almost, or the heat flow that comes from the inside is pretty low. That means every time you get radiation to the sky during the nights, as you have with a car or something like that, your surface overcools. It's getting colder than the ambient air. And that during the night when the dew point is already pretty high. So what you get is condensation at the exterior surface. If you have a facade that can handle it, it's not a problem, but you will at the same time find some microbial growth. So the only way dealing with it until now is that we add biocides in our paint coats or whatever. Otherwise, you get that condensation. If you have a surface that absorbs water, that can help. Because as soon as that condensation is absorbed, it's not available anymore for any microbes that might want to settle there. On the other hand, if you have an absorbing surface and you have high driving rain load, then this will also get wet enough, and then again, algae and so on can grow. So it's always a question, what you want to do, what is your climate, and how can you deal with that? And one possibility to fight against that overcooling effect that leads to condensation is that you have a low E coating. So that has a low thermal emissivity, and therefore that exterior surface stays warmer. That's one thing that we tested there, among others. Another interesting study, and there were several studies that we did in our field, was on pitched roofs that are insulated, like cathedral ceilings, something like that here. So people are actually living in these roof space, it's not an uninhabited attic. So if you want to live there, you have to insulate it. And people always thought, well, if you do this, you might get condensation at the under roof or something like that, and therefore you have to ventilate that. Yeah? So natural ventilation of roofs. But if you have a ventilation space in between rafters, then the insulation you can put in is limited. Yeah? It would be better to fill it up. It's also better to fill it up because if there's a ventilation gap there, a space, then insects can get in there, rodents and other stuff that you don't want to have there. So you need to put chemicals inside in order to avoid it. So it's better if you could insulate the whole thing. And there was an innovation coming up, you might have heard of Tyvek, that was a vapor permeable waterproof layer, you could say. And because it was vapor permeable, we got diffusion towards the outside, it was vapor open, so no problem with condensation. And it actually turned out that the roof stayed drier than when you ventilated. And we had a very long dispute with the trades about that, carpenters, roofers, and so on, who always said, no, we don't want to do it. We are sure our tradition has shown that the roofs, the ventilated roofs, work well. We don't know whether that new type of structure will also work. And we're sure that they work well. And I told them, no, you don't have any experience with that because the roofs you're building now are not the roofs that we built 10 years ago. 10 years ago, we put maybe 4 centimeters of insulation on site. That's not much. Now it's 20 or 30. And it's not the same roof again anymore. It has changed completely. Because now you get surface temperatures that fall below the dew point almost every night. And you ventilate in wintertime more moisture in than you get out. And our tests could prove that. And it took a while, but I think now most people build these unventilated roofs that are vapor open at the exterior. So that was a quite interesting dispute in the beginning, and now I think everybody's on the same page, at least in Germany. Many other countries it might still be different. Another topic, I didn't touch anything.
That's all right. That's all right.
And so for us, it's not only that we want to preserve them because they are nice to look at, it's also an economic factor. So we had quite a few projects from the government in order to find out what we can do because we have a saying with these heritage buildings, they say, use them or lose them. That means if you don't use them anymore, then nobody cares about it and then they will be gone sooner or later. But if you want to use them, then they have to be up to the modern standards, comfort standards. Nobody wants to live in a house that's not heatable in wintertime, it's too cold, too moist, too I don't know what. Therefore, we have to insulate them, and that's pretty tricky because these buildings are very moisture sensitive. You really have to know what you're doing because if you don't do it right the first time, then they might be lost. So we did many investigations in that field too. Yeah, and what you need, because you can do a lot of measurements, but it's also good.
Sorry, we just lost that's all right. We just lost our, we've got 14 people who aren't here at the moment.
Okay. So, and now I'm talking about a model, and also Jesse Clarke will later on show you more about that. Instead of measuring everything, you can also do simulations. You can simulate what's actually going on in your building shell. You look at the temperature and the humidities, and I will show you how it works, or what you can see. And that was pretty successful worldwide. We have a lot of clients in Germany because Germans want to have durable buildings, so it is quite obvious that you need to do something about the moisture because most, and that's still the case, the single most important reason for damage in buildings is still moisture, even in Germany, even after so many years of research and so on. And in the United States, they also had a problem because their buildings became more and more energy efficient. Their HVAC systems became more and more energy efficient. And then they developed mold growth. They got problems as we had, but they didn't have any tools to find solutions or to find out who's to blame. And there was this saying among lawyers, mold is gold. Yeah? If you find mold, because it's maybe adverse to your health, you can make a lot of money with that. And builders were really scared and tried to find solutions that prevented mold growth or interstitial concession. Yes, please.
Has this been worked or compared against or validated using CFD?
Against?
For CFD, computational fluid dynamics?
This is not really computational fluid dynamics because there's not that much air movement going on, at least should not. Yeah? And I think CFD simulations in the building shell are quite complicated because you don't really know where the flow passes are. Yeah? We are working with CFD. We've done this also for the aeronautic industry, but here in WUFI, there's no CFD. We simulate in a different way. Yeah? We have field data, and I show you just the next.
I'm just talking about the validation of the testing.
Yeah. Well, validation. This is a model. It's based on my PhD thesis, where you just look at heat and moisture flows through porous building materials. Yeah? This is what you can see here. I don't have the same slide here, so therefore I cannot really take this now. What you see here is a cavity wall. It's a typical German cavity wall where you have a masonry wise at the interior, and here this is the rain screen, mostly brick veneer or something like that. And what you see here is over a day the temperature distribution. When the surface heats up, it goes up and then it goes down again. This is the insulation layer, mineral wool insulation. You see there's the largest temperature gradient. And here at the interfaces and at the surfaces, you see the heat flow in and out. What you see here is the same thing for the relative humidity. That's that green line here. And for the water content, that's that blue line. So every time it's raining, the water content rises, also the relative humidity rises. But then here in this interior wise, the relative humidity is pretty low. It's about 50%. So that stays dry. And in order to do a simulation like that, you need some more material data than when you just do a dew-point calculation. And Jesse will talk more about it. But most of the time, you have most of the data you can find in the material database of WUFI. Not sure whether that works because I don't see the new slides here, but they see it. Okay, fine. But if I don't see it, I always have to turn the back to you. Okay, what you can do if you have such a tool, you can say, I do a WUFI simulation in all my different building assemblies and bring them together to the interior spaces. So I have a whole building simulation tool, but not just energy simulation, also moisture simulation, so whole building hygrothermal simulation tool. That helps you also to show how the walls interact with the indoor environment, the indoor climate, especially when you have moisture buffering materials, then your moisture or humidity swings will be much lower inside than on the outside, for instance. And you also have here, I think you can see that here, all the heating systems, TV or whatever you want, that you can tie into that. And talking about collaborations, for WUFI as a whole, we have many collaboration partners all over the world. Finland, Japan, Norway, Clima, here, this is in Korea, but also here in Australia. don't find it on this one, but they're also here for Australia and New Zealand. Our cooperation partner, France, is a cooperation partner for WUFI and all the others see here. And one of the most important ones is also Oak Ridge National Lab, because we worked extensively together with the Americans. And I think that was very fruitful for both of us. I will explain later on why. Because the difference is we knew more about moisture control and things like that, and they knew much more about climate, because in Germany we have one single climate zone, you could say. And that you can get problems in other climate zones, I didn't know. I know now, and I know that in hot and humid climates, the moisture problems are even greater than in cold climates, which is also interesting and keeps us busy. And we also have a cooperation with FIOS, that's the Passive House Institute of the United States. And we provide for them a tool, WUFI Passive, that's also to certify their billing. So that's an alternative to PHPP that many of you might know. I don't know whether you know the history about this, why it came to that, why they separated from the German institute in Darmstadt. One reason was that it didn't agree upon the requirements for the different climate zones, because they said the requirements that you have cannot be the same in Germany and all over the world. It has to be climate dependent. But I don't want to go into more detail here. So if you do a hygrothermal simulation, then the question is always, do I have a problem or don't I have a problem? Of course, if I get condensation, I have a problem. But most of the time, you find mold growth without having any condensation, because mold doesn't need liquid water. It's enough when the relative humidity is high enough. And I think, now it works again. You see that pointer? No, I have to show it like that. You see here, germination of the mold spores and growth rate can already start below 75%. This is rare, it's not for every species like that, but you can be sure if you are above 80% longer periods of time that you will get mold growth. And you see that mold growth is also dependent on the temperature, and that's a tricky thing. While this kind of mold doesn't grow at all if your temperature is below 10 degrees. There are others that grow. But all of them grow much more slowly. It takes much more time for them to germinate. That's the reason why we put our food in the fridge. It takes more time until mold develops. On the other hand, you can see when it's pretty warm, around 30 degrees, it develops very fast. And that's a problem in humid climates. You have a high humidity and you have a high temperature, and therefore that's the best thing that can happen to mold. We measured also that in our institute in order to know at what stage or under what conditions mold will grow and what species. There are different ones. There are some that are really dangerous for your house and others are more harmless. And luckily, the more dangerous ones need a higher relative humidity than the other ones. Okay, and we have a mold growth model that is at least can show you what the risk is. And there's also something like that, an evaluation for mold in the ASHRAE standard, and I think Jesse will talk about this, that we recommend for use also in Australia and New Zealand. When you do simulations, and also to certify materials, you need to do measurements of the thermal conductivity. This is done in our laboratory. So we have a part of the laboratory in Stuttgart that determines all the thermal characteristics. And we have another one in Holzkirchen at the field test site where we look more at the moisture characteristics. How much moisture is absorbed, how fast is it absorbed, what's the vapor diffusion resistance of a material, all that is measured there. And we even have an NMR scanner that shows us the moisture distribution in such a sample as you can see see it here, without being forced to cut it up in pieces and dry it. So you can do this on a continuous basis, which is a quite good thing. Then aging is important. Durability is something that we think is very important, and durability depends on moisture, but also on radiation. So UV light, for instance, also when you have heating up of facades due to radiation in one part, and the other part is because it's in the shade, it's too cold, you might get tensions and problems like that, and if this happens very often, then you might get problems. Also, that is tested in our laboratories. I have here one slide that says lessons learned, and that's something where we found out. This was an installation that we had, and we tried to see what's happening if you get airflow through your milling components. And the question was, where does that condensation or whatever we get condensate end up? And also, do you get a lot or not? There were different theories in the beginning. We thought, well, if you have straight flow, that flow path in the insulation layer will heat up and you don't get any condensation. The other theory was, well, could also be that you have a more tortured path and that the air stays, the humid air, a long time in contact with the exterior cold surface and you get a lot of condensation. Now, in order to find out what is true, we did this test. And you see here, it's condensation all over. This was vapor tight here, perspex glass or something like that. Perspex? Polyethylene, yeah, something like that. So you could see what's happening on the other side. And you see there's a lot of condensation. And the real problem arose when we sealed those two holes, or at least the interior hole we sealed, we still pulled air out of that here, and we still got condensation. So now the question was, where does that come from? And the thing is, it goes through the tape joints of the sealing tape. So a sealing tape is never completely airtight. It's very little that goes through it, but there is some airflow going through it. So you will always get some condensation, but that's only a problem if it cannot dry out again. As long as the whole assembly is pretty vapor open, it's no problem at all, it can dry out. Only when you have two very vapor tight layers on both sides, you might get into trouble. Okay, and you've all learned that airtightness is very important for energy savings, but it's also important for moisture control. It's not only energy that you're losing, it's also maybe your whole building assembly that you're losing when it's getting wet. Yeah, these are some more exterior investigations on different external insulation systems. I want to jump over that. What's also important that we have quite a bit of scientific exchange with other partners, especially with the United States. I think also companies should do that because that's very important that people know how to install insulation, how to tape it and so on in order to make our systems work. It says here now, welcome to PC Hub, and it doesn't do anything anymore. I'm really sorry. If I get more time, then that's okay.
Yeah. That's right. Take as long as you like.
So the next slide, we can go over that pretty quickly. It just shows you that we work together with scientists all over the world, also in China. And we had a Chinese company that wanted to build up their own laboratory there for building physics. and they were so fascinated our building or wanted to just copy it somehow. And when we went there, we found exactly the same building close to Shanghai. Now it works. Yeah, here you can see it. So this is the main entrance of our building, and this is something we have up there, a large conference hall, and this is what they built close to Shanghai. Pretty much the same thing. I thought that was funny. Another thing that's important when you have a tool that helps you to understand moisture control and you have a problem, you can try with that tool to solve the problem. You can mimic vapor control layers that don't exist. But you could say, well, if I had a vapor control layer that's like this one here, as a vapor diffusion resistance that depends on the relative humidity. And I knew at that time that there were some materials, polymer materials that had this characteristic. So you cannot patent an idea. You need to have a solution, technical solution. And then we were looking for something and we found something. It was a nylon film at that time. And Intello is, you could say, something similar, an improved version of what we had at that time. And another, I'm not talking about the chilled water wall now because that's something, you will see that here as well. Most of these materials on the market that have a considerable market share, it's not a large one, but that you can already feel are wood-based materials. Wood fiberboard and things like that, you all know that. On the other hand, with wood, so I go here or where is it? No. Yep. No? No. It just changes that, doesn't change that. Okay. So, I think.
Yeah, you change that there.
But it doesn't change. Okay, it changes there, but I don't see it. Does that? What do you mean? What's that about? Okay. Yeah. Now let me talk about that. So we will run out of wood sooner or later. We already have a problem. Wood prices have gone up, at least in Europe. That's a problem. And most building materials, most insulation materials are still based on oil and things like that. Yeah? So on fossil fuels, and they're not renewable. So now the question is, are there alternatives to wood? If you don't have enough wood or we need wood as structural members, are there alternatives? And we think there are. And we found that that's a material that is called, or it's a plant that is called bulrush in the UK and cattail in the United States. And it has some quite interesting characteristics. First of all, it grows in the wetlands and is therefore also very resistant to mold. That's a good thing, especially once. Okay, if I want to go back, I have to go there. That was one too far. Okay, two too far. So that is the material here. And the interesting thing is its spongy interior. The spongy texture of its interior is like an insulation material. So like a natural insulation material. And you can make boards out of that that have pretty good insulation properties. So that would be an alternative. Grows much faster than wood. I think 3 to 4 times the plant mass it has compared to wood. And it grows on land that is not very useful, wetlands. Yeah? So that's an interesting thing that we are working with at the moment. And now to finish all that, just want to show you what we think is important when you do design of a building. And that's something we developed together with FIOS in the United States. Of course, comfort is the most important thing. Carbon footprint is important. Cost effectiveness and resilience. Resilience means if there is a problem, it's easy to repair. Not the whole building will be lost. And then, of course, and you all know that, this is passive house concept. You need radiation control, shading. You need an airtight building, and then you need ventilation. And the best thing is if you have ventilation with energy recovery or enthalpy recovery. That means also in more humid climates that you exchange the humidity. Then if you have a cold climate, you need high performance insulation, and you have to care about the thermal bridges. If it's more moderate temperate climate, it's good to do it, but might not be completely necessary. Then I think also the storage capacity of your building and your building components is important. It's as well the thermal storage, everybody knows about that, but also the moisture storage can be important to have a dampening of humidity swings that you would get, because as soon as you air condition your building, and you do this during daytime, you extract a lot of moisture. And during nighttime, when the air conditioning is shut off, the humidity goes up again. Because you produce moisture, you get moisture due to air infiltration, so it goes up again. And can reach levels that are uncomfortable and maybe not, or might even provoke mold growth. So it's good to have some buffering capacity. That stabilizes these humidity swings between day and night. And another very important feature is, of course, moisture control. That's something that's missing when you look at any other charts like that. That people just don't think about it, but moisture control is important to contain the relative humidity indoors and also to avoid moisture problems in your building component. Now, I show you some examples of WUFI. WUFI will be explained to you later on a little bit more by Jesse. Yeah. And I think it's important to know how well does it work. Is what I simulate realistic? And you will see in the next slides, here we had two natural stone materials glued to each other, and we want to see what the water uptake is, and we always calculated that and measured it. You see here, the dots are the measurement points, the solid lines are the calculations, so it's an almost perfect fit. Then we used our NMR scanner and put it through, and you see again, dotted and solid lines and dotted points, it's almost perfect. So if you know what your boundary conditions are, which is easy here, and you know your material properties, you get very accurate results. We did the same thing in our filter site in that air-conditioned test hall, where we had these samples here. Those samples we could take out and weigh them. And this is what we did. You see again, up there is what you see. Is there the, well, I show it to you like that. These are the climate data that we measured. This is here. We built them in when they're completely dry, and then they took up some moisture every time it was raining. You see it here. A lot of wind-driven rain. Get that chunk here, and then it dries out again. And we were also looking at the moisture profiles with our NMR scanner, and you see again a perfect fit. So that works pretty well. Here the governing transport is liquid flow, but it's not only liquid flow. Always, as soon as everything gets dry, you get evaporation, and that's mostly vapor diffusion. Go through that more quickly. Something similar there, where we had different types of brick veneer, water repellent and not water repellent. And again, you see from the initial moisture that we had, how it turns out. Again, the dots are the measurements, and the solid lines is the simulation. Works pretty well. That's a similar thing. That is a masonry wall with external insulation on top of it. And you see how this dries out. And it's interesting how it dries out. When you have your mineral fiber insulation, it dries out to both sides. You can see that, and pretty fast. If you have polystyrene insulation, which is more vapor retarding, the mineral fiber, it dries out only towards the interior. So if you have an external insulation layer, then of course it keeps the ball warmer, but if moisture gets behind it, it dries very slowly. And that's a problem we will see later on. Yeah, I was already talking about these green roofs. And there's a thing we had in Germany, a lot of problems with leaky flat roofs. When your flat roof is leaky, then you get a wet insulation. So now there are two possibilities. Either you take all that insulation out and try it again, or you say, well, I just put a better roofing membrane on top of it, and I protect this roofing membrane by an insulation layer, usually extruded polystyrene. Leave all the moisture in. If you have a good load-bearing structure, that's not a problem. Yeah. I also save the costs for getting rid of all that wet insulation. It stays in there. It still has some insulation capacity. Even the wet insulation is better than no insulation. That's quite important. And you add some. So we did this, and then only to find out it works very well when you have gravel or something like that on it. But as soon as you have plants on it, and substrate that retains the moisture, because otherwise the plants can't grow, then your insulation tends to pick up moisture. The question was how much? We thought it's difficult to say. The manufacturer said, oh, no, that won't get more than that. 3 or so is maximum. That's not a lot. So what we did, we simulated it, but we had no idea actually what are the boundary conditions in that substrate. So we assumed it could be something between 85 and 100% on average. And we found, okay, if you have 100 or 95, you get this moisture uptake, moisture accumulation in the slabs, but over a period of 30 years, it's not that much. The question is, how long do you want your roof to last? It will last much longer because it's now well protected by that insulation layer, the roofing membrane, which is a good thing. So in order to figure out what was actually the case, we did then measurements, because now we knew, due to that parametric study, we knew what was the deciding factor for that moisture accumulation, and that was the humidity in that substrate layer for the plants. So we measured here the dew point and the temperature. We had, here you see that installation. These are the different roofs we looked at, and there was one reference roof that just had gravel or pebbles on it, where we knew that there's not a problem. And these are the results. You see, July, August, we had hardly any rain, and you see that the temperature of the reference room was most of the time well above the dew point temperature. That means it was dry up there. If you took the two green roofs, you see that they're always coinciding. So if temperature and dew point temperature are always the same, it means you have 100% relative humidity, or maybe 99, but a pretty high relative humidity. Later I found out that the roots of plants like grass can only extract moisture from a substrate when it's what they call there the water activity or something like that is about the same as 99% relative humidity. So that proved that we were right here, and you get that moisture accumulation. And then you can do simulations and find out if you have a thicker insulation, it takes much longer until you can see, of course, if you have a moisture accumulation, then this will reduce your R value. But this process is much slower when you have thicker insulation. Here we had just 8 centimeters. You would nowadays put 20 or something like that. And then it can last or can be an effective insulation for 50 years or longer. And most of these roofs won't live longer anyway. So I think that's quite good. Now, you might have more lightweight flat roofs, and they're also interesting. The question here was, what happens if while I close the roof, it's raining? What happens with that water that went inside? And the theory was, this is the roof that we looked at. It had a vapor barrier at the interior side, as they take quite often aluminium foil, then installation of the mineral fiber insulation. We installed temperature and humidity sensors to find out what's happening there. And we recorded that. And we also sprayed upon water. We wanted to get about 2 kilograms or 2 liters per square meter in it. And then we wanted to see what's going to happen. When we opened up the roof after 3 years, there was still water inside. So that was a surprise to some of the roofers and also to the manufacturer of that material, because they said, well, you get so high surface temperatures. And if it's warm, the water will just leave that roof by vapor convection, because you get such a high partial vapor pressure. Now the question is, why didn't it dry out? And we looked at the roof surface temperatures, you compare to the ambient air, and well, really, you get summertime temperatures of 70 degrees, sometimes even more. So that should be enough to dry out the roof, but it wasn't. During the nights, you see, and this is the same here, that your roof surface can fall, or its temperature can fall or drop well below ambient air temperature. We measured up to 10 Kelvin, 10 degrees C difference. So even in summertime, you can sometimes get ice formation on such a roof when you have a cold night. And yeah, these are temperature fluctuations. I go over it. Now I want you to concentrate, first of all, here on the right-hand side. The blue is the relative humidity. These are the scales on the right. This is the temperature is red. First of all, it's measured and simulated. The thicker solid lines are the measurements, the thinner ones the calculation, and you see principally a pretty good fit. There's some deviation here, the temperature here, where we measure 0 degrees and simulate more, 20. And the reason is that there was snow on the roof. And that's something we cannot simulate. We don't know whether there's snow or not. If there's snow on the roof, then the temperature stays at 0 degrees, while WUFI would assume that it's getting a bit warmer. We see that, and that was measured just beneath the roofing membrane, that we have 100% relative humidity. Well, this is what you would expect. All the moisture is hanging up there, and it's not a big problem. If you look at the summer situation, you see every time the roof heats up, the humidity under the roofing membrane goes down. So moisture is moving inward by vapor diffusion. And that explains now why it didn't dry out, because the moisture never saw the 70 degrees. As soon as it got warm up there, it went down to the other side. So the maximum temperature the moisture sees is 25 degrees, and that's not a temperature where you have a very high partial vapor pressure that will dry out the roof by vapor drive or something like that. What happens if that moisture is moving up and down? We had one part painted in white to see what that effect would be, and then we looked at the surface temperature and how this was changing over time. And you can imagine, when you have a dark roof, that this moisture moving up and down is also a kind of heat transport, because it evaporates at one side and condenses at the other side. And you've probably heard of that this latent heat transport can be quite important when you have very vapor permeable insulation materials. So in order not to be too long, started 12:15. The final story, and that's the story about investigations we did on cavity walls. In the UK, they have a lot of these cavity walls, also in northern parts of Germany. And the cavity wall is such that you have the interior wise and you have a brick veneer on the outside. And in between, insulation. And the rule was that you had to leave at least 2 to 4 centimeters ventilation gap, rear ventilation, behind the exterior wise. Otherwise, people were afraid that the whole insulation will get soaked with water. The problem is, if you want to retrofit such a cavity insulation, it's very difficult to leave that 2 to 4 centimeter layer, because you fill in some kind of insulation material and then the whole cavity will be filled, will be completely filled. And another problem is, if you leave that air layer, then you can put in less insulation. So the thermal quality is less. So the idea was, let's fill up the whole cavity. And here we did these investigations, and we found out if you compare ventilated and non-ventilated, fully filled cavities or cavity walls, then there is only minor effect. Doesn't really matter. So the conclusion was, we fill it up. That's the best thing, and we still believe in that, Germany. And with that belief, I went to the United States, and they told me, no, you can't do that. It doesn't work. I said, well, we've tested it. So, maybe the climate is different. I said, no, of course, that was done in Waterloo, Canada. Of course, they have colder winters, but I thought, it doesn't really matter whether you have minus 20 degrees or only plus 5 degrees, it's always below the dew point. And there may be a smaller difference, but not the difference that we say here works and here doesn't. But they had measurements to prove it, that it works much better when you have much fewer problems when you ventilate. Rear ventilated exterior brick veneer. So we did simulations with our wall. And this is now the summertime situation. We're of course more looking to the wintertime in that period, and then figured out the summertime is a problem. And I don't know whether you see it here. The brick veneer is wet. When the sun shines on it, and you get vapor diffusion towards the interior. You can see it here. The vapor flow every once in a while, and the humidity is rising. Also here, the water content at that interior-wise is rising. But who cares? Now, what is it? 10% by volume? 100 kilogram per cubic meter, but only here. At the exterior layer of that interior wise, it doesn't really affect the whole construction. And then in winter time, it dries out again. So, works perfectly. But now we could imagine if that wasn't a masonry wall, but a wooden structure, then the 10% by volume is maybe a little bit too much. And that's exactly it. That's the reason. We were looking for a reason in wintertime, but it had nothing to do with winter. We need this ventilation gap because of the summer conditions. And in Germany, we have, or also in the UK, a very moisture tolerant structure. As soon as you replace that masonry with a wooden structure, then it's a different story. And therefore, now we also believe that if you do it with a wooden structure, you need ventilation in order to reduce the amount of moisture that you get in there. So, yeah, and this was also tested in Seattle, Washington, State University. Yeah, that's it. We're doing that together with them. And Here they didn't have brick veneer, but a water absorbing mortar, which is as bad as brick veneer from that point of view. And we got measurement results, and we also okay. Now, and we measured here the vapor pressure in that ventilation gap with and without ventilation, and we also simulated it. And you see that the vapor pressure when you have ventilation is much lower in that cavity. So also what the interior surface sees from the wooden structure, the exterior surface of the wooden structure is much lower vapor pressure. And you can really see that there is a difference that you can also simulate. So also that the ventilation you can simulate, and you see this is something where the simulations help you to find the reasons why things work in one place and they don't in others. And not only to find out later on, because then you know it already, also you could predict that if you go to another climate zone, if you have another construction, you could find out with such a simulation, will it work or won't it? Thank you.